Your phone charger is sitting in the wall right now, nothing plugged into it, and it's warm, maybe even hot. Most people shrug it off. By the end of this video, you won't. Here's what we're covering: why your charger gets hot doing nothing, what it's costing you per year, and why that heat is slowly killing the charger from the inside. Let's start with money. A typical charger on standby draws around 0.3 watts. That's roughly 2.6 kilowatts per year. At the US average of 0.13 per kilowatt, that's 0.34 per charger per year. Sounds like nothing. But most households have 5 or 6 plugged in constantly. That's nearly $2 a year just from chargers. Add your TV standby, microwave display, router, laptop brick. You're easily at $10-15 a year for electricity you're getting nothing from. Nobody calculates this. Energy companies love that. So why isn't the charger consuming anything when nothing's connected? Inside that plastic shell is a switched mode power supply, a transformer, a control chip, capacitors, and switching transistors. It takes 120 volt AC from your wall, chops it up at high frequency, steps it down, and outputs clean DC for your phone. Elegant design, but most of it never fully shuts down. The main heat source is the transformer. It works by magnetizing and demagnetizing a small ferrite core between 65,000 and 130,000 times per second. Every cycle loses some energy as heat. This is called core loss, and it happens whether your phone is connected or not. The transformer is cycling its magnetic field 100,000 times a second, generating heat, producing zero useful output. That warmth you feel? That's it. The control chip makes it worse. Its job is to detect whether a device has been connected, so at idle it constantly sends out small polling signals, pinging the output every few milliseconds asking, is something there? If you put an oscilloscope on an idle charger, you'd actually see these pulses. The charger never truly sleeps. It needs to respond instantly when you plug something in. Cheap chargers skip the burst mode optimization that reduces this polling, which is why budget chargers run hotter at idle than quality ones. Here's where it gets serious: that heat is actively destroying part of the charger. The capacitors inside are rated 85 degauss. Most people read that as safe up to 85 degauss, but that's the maximum, not the target. Ideal is around 40 in 50 degauss. The rule: for every 10 degauss above ideal, the capacitor's lifespan roughly halves. If your charger sits at 60 degauss internally, completely realistic for a cheap charger in a warm room, that capacitor is aging 4 times faster than it should. As it degrades, it gets worse at smoothing current. More ripple current flows through it. More ripple generates more heat. More heat degrades it faster. It's a feedback loop that starts on day one. This is why cheap chargers die in a year or two while quality ones last 5 or 6. Efficiency labels don't help you here either. Those ratings are measured under load, while the charger is actively charging something. Standby consumption is tested separately, with limits up to 100 milliwatts. The label on the box tells you almost nothing about what the charger is doing. The other 20 hours a day it sits idle. Audio clue worth knowing: if your charger makes a faint, high-pitched whine in the 6,000-15,000 Hz range, that's the transformer physically vibrating at its switching frequency. It means higher core loss, more heat, faster degradation. Not immediately dangerous, but a warning sign. This is what GaN technology solves. Traditional chargers use silicon transistors, which lose energy as heat during every switching transition. Switch faster, more transitions, more heat. Gallium nitride transistors switch faster with far less energy lost per transition. So GaN chargers run at higher frequencies while generating significantly less heat. Less heat means slower capacitor degradation and longer lifespan. If you leave chargers plugged in all the time, a quality GaN charger is one of a few hardware purchases that genuinely pays for itself. Quick summary: your charger is hot because the transformer is magnetizing 100,000 times a second with nothing connected. The control chip never stops scanning. That heat is killing the capacitors in a slow feedback loop, and GaN fixes this with better switching physics. You started this thinking a warm charger was harmless. Now you know exactly what's happening inside it.